graduating in next months, hopefully. For good luck for that already. In Italian Institute of Technology. She is graduated from Koç University Electrical Engineering department, and also did her master thesis as well in Koç University in biomedical engineering. Then moved to Italy after a small startup or industry experience, let's say, in robotics. She is now currently working on human-robot interaction and manipulation, different manipulation concepts. And I will leave the stage to her to share her work with us. You can present your work, Idil. Thank you.
Thank you very much for this kind introduction. Let me share my screen and start presenting all of you. Okay, you could see my slides, right? Here on the side, you see a picture taken when I first joined the Italian Institute of Technology. As you can see from this picture, I am fully committed to bringing robots in our daily lives in most literal sense. And you could say my research is quite directly hands-on. The topic I am going to cover today is integrating perception-informed adaptation into contact-rich control for collaborative and autonomous settings. In my research, I had the opportunity to work with various kinds of robots to establish effective, safe, and contact-rich interaction, not only between human and robots, but also between robots and their environments. From the human point of view, these interactions can range from no physical contact to direct contact. From the robot point of view, they involve different levels of autonomy, extending from telemanipulated actions to fully autonomous ones. Therefore, I divided my talk in 4 main categories: telemanipulation, collaborative carrying, assistive robotics, and non-prehensile manipulation. So let's start with our first subcategory, telemanipulation. The essence of telemanipulation is captivating, owing to integrate human cognitive skills into the system, especially in unknown, hazardous, or dynamic environments. Nowadays, the technological advancements in collaborative robot technology and motion capture system reduce the classical limitations of effective teleoperation and renew the interest. Recently, bimanual manipulation becomes very popular. Here, the dual-arm manipulators are coordinated to achieve a mutual goal. But with the increase of task complexity, the simultaneous use and coordination of multiple robotic arms is necessary. To this end, a shared control concept has been introduced. It empowers the robot to operate with a degree of autonomy, hence reduces the user cognitive load. However, very few studies focus on employing more than 2 robots. For instance, a multi-robot data collection platform developed for gathering demonstrations to coordinate the arms, but only validated in simulation. Another work aimed to increase robots' manipulability index, while the object was assumed to be already grasped. In realistic applications, it is better to cover the situations like approaching, grasping, and releasing. To sum up, the question we seek to answer are: is it achievable to control any number of robots intuitively? Can it be accommodating even for the naive users too? And if so, how? In response to that, we propose a novel telemanipulation framework that enables both the individual and combined control of any number of robotic arms. In the different phases of our reconfigurable system, each robot could act as an independent arm or one of a pair of cooperating arms. Moreover, the integrated teleimpedance paradigm into the framework addresses to perform complex tasks with better safety, adaptability, and efficiency. The framework here have three control modalities, and it enables users to control subgroup of arms with the selected control modality according to the task. The goal of the independent control strategy here is to mimic human hand motion with the selected robot. Then, when the control starts, the initial relative transformation between hand and robot end effectors are collected to map the hand pose and the robot, given in the gray boxes here in the equations. And after that, the continuous hand rotation and translation highlighted with red here are used to obtain robot desired poses. Here in this video shows how a robot group moves with independent control strategy. When the coordinated control is initialized, the robots are linked to a virtual frame created at the midpoint of the robots. And the hand is also linked to this virtual frame by using initial transformation again. And the motion of the virtual frame is controlled by the human continuously. Moreover, the user can regulate the distance between the robots with the joystick. Here in the video, you can show how a robot group move if this strategy is selected. For both control strategy, robot stiffness are regulated through mimicking the stiffness profile of the user arm or muscles. I will explain how we did it. When dealing with multiple manipulators, one can advantage from keeping the robot at a definite position. If the user enters freeze state, the robot's poses and stiffness remain constant. The robot group and the last used control strategy are preserved. With this, when the system is unfrozen, the users can continue from where they left off. Here, you can see the user enters a freeze state. I would like to elaborate more the reconfigurability of our system. This video shows how a robot group with 4 arms can be controlled. Moreover, the operator can intuitively switch the hand that is responsible for the motion of the group. Here, the right hand controls the robot group, 2 robots, while the left hand controls the other simultaneously. On top of this, the robots can be seamlessly combined to form a single robot group. In last scenario, where the user control a robot group with 3 robots with 1 arm and 1 robot, and then combine again and enters a freeze state. Here you can see the experimental setup we used for the evaluation of our proposed framework. The Maya arm bands, which were placed at the forearm of the user here, are used to regulate the robot's impedance profile, like mimicking our muscle stiffness. Also, a graphical user interface was provided to the user in order to monitor their current selections. The experiments we conducted with 12 naive volunteers who had not teleoperated the collaborative robot arm before. The first subtask includes placing a box and performing Peggle hole task representing complex interaction with the environment. And in the second subtask, the palette must be held from the suitable locations of the palette and then lift it and translate it as you see and then put it back while avoiding the obstacle. Let's look at what are the outcomes from this work. During the experiments, participants choose independent control over coordinated control in more dexterous parts with employing specific robot that can reach the box and the pack on the other side. Consequently, this led us to have a wider workspace area. We observed that general tendency was to enter freeze state, position the hand in more advantageous position, and then continue to do the task. Then robots are brought to the desired points of the bulky pallet and grasp it. For the manipulation of the bulky pallet, mainly coordinated control strategy was selected. Here users can focus on the motion of the object, the pallet, instead of individual positions of the robot. Lastly, the participants filled out a system usability scale questionnaire. This questionnaire is commonly used to evaluate performance of the system in terms of effectiveness, efficiency, and overall ease of use. The average percentage ranking that we get was 81. It allows us to label our framework between good and excellent in this scale. And this label by definition implies that the system is well integrated, not complex, and a short familiarization period is enough to adapt from the user side. And this is also supported by the decrease in the completion time of the users in the second repetition. While we were watching the casual fun times that I spent with the robots, I want to summarize the overall framework again. We have developed a novel multi-arm manipulation framework that provides intuitive control of both individual and various combination of any number of robotic arms. Moreover, we demonstrated that the advantage of having different control modalities and multi-robot control. Besides, the employed teleimpedance paradigm, which was a constructive complementary of our system, may ease the complex interaction with the remote environment. Now, another research area that attracts a lot of attention is collaborative caring, of course. It centers on the dynamic synchronization of human-robot dyads and offers promising solutions for minimizing user discomfort in especially industrial environments. Building on this motivation, one major challenge in collaborative carrying arises when a large object obstructs the operator view of the surrounding. During the transportation, such occlusions can weaken the human leader's decision-making capability. Consequently, it increases the risk of collision. To address this issue, our study proposed a situational awareness framework for collaborative transportation tasks. It composed of three main components: the end effector dynamics here, the obstacle feedback module, and the whole body controller. The whole body controller calculates a reference velocity, allowing a standard admittance control law based on the force transmitted through the object in between. The obstacle feedback module aims to augment the human partner's sensations and yields awareness of the obstacles around. This augmentation realized through the proposed vibratactile warning and visual fixture unit. The vibratactile warning unit starts to generate warning vibrations via ergo tags. It's placed on the belt of the human to convey information about the location and proximity of the obstacles before the human-robot dyad gets dangerously close to any of the obstacles around. On the other hand, virtual fixture unit restricts the team's movement in the direction of the potential collision, only that direction. Particularly, it activates only when the distance to the obstacle is critically close, like we are really close hitting them. Lastly, the whole body controller generates the required joint velocities of the robotic platform using the desired velocity obtained from the obstacle feedback module. Before sharing the controlled experiments that we did, I wanted to first give a short demonstration that captures the overall idea, which is the dynamic obstacle case is the most challenging scenario, one of the most challenging scenario. As you can see, when she entered the workspace, the robot immediately perceived the change and started to create a vibration. Here is the vibration activated, and the virtual fixture also just restricts to go that direction and just not allows to hit anything around. Now let's look at our controlled experiments where we systematically analyze each feedback modality and their combinations as well. We conducted co-transportation experiment with 4 different conditions. First, a baseline with no feedback. So it was clear that there's gonna be a collision since the operator has no idea from the backside of the robot. But as you also know, the reviewers want that kind of a baseline for a start. then we only activate the vibratactile warning unit. And of course, we change the obstacle positions to eliminate any memorization in the experiments. And then here you see we have a vibration in the right, and because since there's a glass there, so there's a vibration in the right, and but there is no vibration in the front, so operator continue to movement. This line in the middle is the goal line. After that, this time you only utilize the virtual fixture, which give the user a sense of resistance, like a kinesthetic feedback to. And then once this virtual fixture on, the user should go another direction and try again and try again. And lastly, we combine both feedback types, and like you can think as there's an early warning with the vibrations, and but if you want to keep go that dangerous place, virtual fixture just restricts the motion. I would like to briefly summarize the quantitative and qualitative results that we had. This success rate indicates the percentage of trials where participants reach the target line without having any collision. As I anticipated, none of the participants were able to complete the task without any feedback. On the other hand, when the virtual fixture was on, all the participants reached the finish line without any collision, so it is working, and it is effective, like a hard safe constraint. But although the vibratactile warning assists the participant by informing them about the objects, it may not entirely avoid collisions. So we see that participants insist to go that direction. As you can see in the third line, there's a 75% success rate. It was a bit shock for us. And let's look at some other performance measures. The mean completion time is higher for virtual fixture and lowest for vibratactile unit. It is the similar pattern emerges for the trajectory length too. This may stem from the activation of the movement restriction. As on the other hand, as a result of the valuable information that vibratactile warning provides about the environment, the need for the virtual fixture activation reduced. So it is a clear indication that participants can make more informed decisions during navigation. The NASA TLX questionnaire was used to evaluate perceived workload. Note that for this metric, higher scores indicate higher mental or physical demand, meaning worse performance. Since none of the participants were managed to reach the target line under baseline conditions, here is the green colored, it has the worst results overall. When we analyze more deeply under virtual fixture condition, participants found the task more physically demanding. This was likely due to the extra effort required when the constraint was on, when the motion is restricted. For the overall workload results, participants clearly preferred having some kind of feedback about the obstacle rather than none. And among all, the combination of both feedback types was favored the most, as it resulted in the lowest perceived workload. For the SAS score, as I explained before, the lowest possible usability has the baseline, while the others were significantly higher. Besides, participants favored the combination of these warning units, so it was the best for the usability. Here comes our last subcategory that include human in the loop. In previous cases, robots often rely on humans, but in assistive scenarios, it is the human who relies on the robot more. Thus, the robot must never let us down. Worldwide, there are more than 300 million people that suffer some kind of a blindness or visual impairment. The use of guide dogs and white chains is widespread, but they come with important limitations. For instance, for guide dogs, they need a constant care, expensive to train, and they cannot make complex decisions beyond their training. And to be honest, this is one of the rare cases where using a robot would be literally cheaper on top of the other advantages, because training a guide dog really money consuming also, and beside number of guide dogs are limited and people wait years sometimes to have one of these. White canes, on the other hand, they're really primitive. It's just a stick and they are limited to the detection range, which they only can touch with it. And the development of assistive robotic systems to guide the visually impaired people has a big potential in order to overcome these limitations. Let's look at what has been done so far in this field. In this field, different versions of assistance have been proposed. For instance, white canes are enriched by sensors and user feedback. Also, physical assistance for keeping the user in balance provided by the robotic canes. And leg robots are employed using leash to guide blind peoples. Or alternatively, drones are physically connected by a cable with the blind users. However, the presented approaches share a considerable limitation. They are really task-oriented and cannot be exploited for the other purposes in their idle times. On the other hand, a mobile manipulator can also be easily employed in other daily living activities. It can lead to increased independence. They can be used as a support for remote care, or it can also function autonomously to carry out other kinds of housework activities. To benefit those advantages, we propose a novel framework that enables a mobile manipulator to plan and execute collision-free trajectories, exploiting local manipulation skills to guide a visually impaired person through an unknown environments. So in this video, you can see that a robot localizes itself within a global plan and continuously updates a collision-free trajectory, the trajectory given in the green color, and guides a visually impaired person through narrow corridors. Given the multiple safety concerns involved, it was crucial to design a robust and reliable framework. The human is in direct physical contact, this time with the robot, and on top of that, we obscured one of the most essential human senses, the ability to see. Also, I would like to mention that this work was the Best Paper Award finalist in ICRA 2024 in Japan. So on the right side, we can see the software architecture behind the framework, divided into three main categories: planning, blue; control, green; and the orange one is the human tracking. I will go the details in upcoming slides, each one of them. This is the high level side. To generate a collision-free path, we employed obstacle avoidance navigation stack using both global and local planner. The goal of the adaptive pulling unit here is within the planning is to prioritize the safety of the human. It keeps the human within robot's collision-free trajectory. This module generates a pulling vector between the desired human pose and the current one. You can see it in the right picture with the red P vector. We are tracking the human legs. So this is the current human position, and the desired one is the collision-free trajectory. The x component of this pulling vector is employed to calculate the gain alpha b that is responsible for regulating the speed of the base, speed of the base. As a result, if the human lags behind, the robot correspondingly reduces its velocity to maintain comfortable walking pace. And the y component of this vector is used for the lateral readjustment of the end effector pose. With this, we were able to keep the human within the safe collision-free region. And also, y component of this vector is used for the computation of the lateral stiffness. We formulated the stiffness profile with a logistic function to ensure a lighter pull if the human deviation is low, but a stronger pull if the deviations are increased. The aim of the human guidance unit is to plan a trajectory that avoids collisions at the same time for the mobile base, the robotic arm, and the user coupled with the system. To do so, 3 desired poses need to be computed. The mobile-based target waypoints is selected among the collision-free poses produced by the obstacle avoidance unit. So the next base target pose is one of the waypoints where D1 distance away. Likewise, the end effector desired pose is selected among the set of previously passed base poses. So since there is no collision there, it's the free to choose, and we pick the ones which D2 distance away from the base. In a similar manner, the human desired pose is chosen as the previously desired end effector poses that lies at D3 distance away. And with this logic, we ensure all desired poses in the system lies within the collision-free area. So this is the framework's control scheme. The admittance controller provides velocity to the mobile base. The ARM's Cartesian impedance controller tuned online by our impedance tuning module. In fact, this unit can independently regulate stiffness and damping parameters along the 3 axes of the impedance ellipsoid located at the end effector of the robot. You can see this is the red sphere that's traveling with the end effector. With axis independent stiffness regulation, we have achieved multiple goals at the same time. First, we kept a stiff profile in the moving direction, principal axis of the movement. It guaranteed a strong pull toward the final location. Second, we gave a motion freedom along the lateral axis when the human pose is close to the desired one. Simultaneously, we made the robot stiffer when it is required to redirect the human on the right track. You can see the adaptive stiffness profile on top. As the human deviates more, then the stiffness increases, and yes. So let's start the experiments that we conducted. We first carried out experiments shaping a predefined trajectory. In this video, we can see the user collides with the obstacles first. When adaptive pulling strategy is on, there is no collision. In the plots, we can see the trajectories of 12 subjects represented with colored lines, and with adaptive pulling strategy, the top figure and the baseline bottom. The black line represents the base pose of the mobile robot. By employing adaptive pulling method, the human pose never extends beyond the robot's base footprint, that is indicated with the gray area. The lateral unintended deviations are compensated by the framework and all components of the human-robot collaborative system. On the other hand, in the baseline plot, the human pose goes beyond like 25% of the time, leading high potential collision risks. And we are never shy to test our framework in more challenging scenarios. Here, it is the one of them. It's an example of navigation in environments containing moving objects like human walkers, and you can see the replaning of collision-free trajectories and real time as green line on top of the video here. And we were able to guide the blindfolded participant without having abrupt or erratic motions, because it's kind of important to test that are we going to adapt this new planned trajectory both with the base and also with this pulling unit at the end effector. If you remember, I previously talked about the state of the art with leg robots or sensorized canes used for the human guidance. However, these systems inherently not capable of protecting the human from the upper body collisions. So in our framework, we achieved full 3D assistance, allowing the robot to support the human both horizontally and vertically as well. Here you can see the key components of the vertical assistance system that we use. We place 3D LiDAR sensor mounted on the back of the robot to detect obstacles on top of the base. The human head is tracked in real time to estimate future collision risks based on the closest obstacle above. And if an obstacle lower than the human standing height is detected, a vertical path is planned first. Then the end effector height is continuously adjusted based on the detected head position and the current closest obstacle height data. In addition, the system dynamically regulates the vertical stiffness as well, following the same logic for the horizontal pulling unit that I explained before. And when the human head position is not sufficiently low, indicating a need for more downward guidance, the vertical stiffness increases, causing the robot arm to pull down more. Altogether, these mechanisms enable smooth 3D adaptive guidance and protects the human upper body as well while maintaining responsive motions for all the environment around. Yes, so this is some showcases. We have a state machine diagram in the right side. You can see now it's free. Now we detect obstacle in the region of interest, it's white, and then it pulls down the human, the participant. In obstacle state, we stay down until there is no collision risk at all. So the system ensures the human passed from that obstacle and then replans an increasing trajectory, and then also still we have this horizontal guidance. In the upcoming video, we will see another emergency state. So here, the human did not bend over. So base is stopped. So we have again safe constraint and pull down more the blind person, blindfolded person. And once the tracked head positions under the obstacle, we continue our motion. We have tested our system multi-subject experiments with obstacle at varying heights. No collision occurred and all subjects consistently remained within the safe region. Also, we again, the participant filled out a SAS questionnaire, system usability scale questionnaire, and the score we obtained was 93, quite high, indicating an excellent level. So, we have reached our final topic. I promise just one last push before we wrap up. And what a coincidence, that's exactly what this topic is all about, pushing. Here, the human is no longer in the loop, and the robot must capable of autonomously execute the tasks. Today, the focus will be more on non-prehensile manipulation, where the robot moves objects through control pushing. Although pushing with legs and arms is an intuitive task for humans, even with objects that have diverse physical characteristics, these skills remain a significant challenge for robots. Some studies have explored pushing strategies that rely on knowing the object-specific properties. They know it, and with using that, they transport the object. In contrast, another line of research focuses on learning how object behave when it is pushed. The idea is to collect hundreds of samples describing how an object moves under different pushing actions. And there are few works that are employ adaptive approaches based on modeling unknown object interactions on the fly, object motion behavior on the fly. And I would like to highlight that much of a state of the art depends on prior knowledge, modeled behavior with simplification that may not always accurately represent the behavior of the objects in real-world pushing scenarios. So to address these challenges at once, we propose a novel reactive pushing strategy. This strategy allows a mobile robot to dynamically adjust its base movements, meaning its linear and angular velocities in real time to achieve successful pushing maneuvers. Notably, our strategy adapts the robot motion based on the changes in the contact location obtained through the tactile sensor covering the base and avoiding dependence on object-related assumption and its model behavior. So it's purely reactive. We inspire from like a bit human, like if we close our eyes and we can push the object with the palm of our hand. So the idea, our initial point was that. The computation of the base velocities relies on two primary input in our system. One, the adaptive rate, derived from the location of the contact point, and the second one is the distance vector connecting the contact point to the target. So we are trying to take the contact point to reach the target. Let's look proposed methodology in more detail. We have formalized an adaptive rate, which is computed on the fly based on the lateral distance between the contact location and the robot center, and a v star velocity scaled with respect to the distance to the target. When the contact point is close to the center, meaning AR close to 0, the robot generates faster forward velocity with the minimal lateral repositioning to reach the target. On the contrary, as the contact point approaches to the edges of the base, so we don't want to lose the contact here, the parameter AR enables higher lateral velocity. This lateral velocity of the base to the sides facilitates a sliding behavior of the object toward the center of the robot base, simultaneously reducing the Vx to prioritize the repositioning behavior more. So this is critical not to lose the contact with the object and having this reactive adjustable autonomy between them. And lastly, in our formulation, the angular velocity of the robot reduces the angular heading error. So in other words, the robot gradually but continuously rotates to align its direction with the target. To demonstrate the robustness of the proposed strategy, we first carried out extensive simulation results. The experiments involved different target points, located the entire vicinity of the robot, two sets of friction coefficients, and three object with varying mass shapes, but the controller doesn't know anything about it. So the colored bar depicts the minimum distance achieved between the contact point and the target location. And as you can understand, we want more blue color rather than the red ones. And we additionally compare our reactive pushing strategy with non-reactive one and a state-of-the-art method akin to ours from the literature, namely adaptive pushing skill. The results show that the proposed strategy exhibited a success rate almost 5 times higher than of its closest competitor. So we deliberately used ungraspable and heavy objects in our real-world experiments. Previous research, this is like 25 kilogram, 30 kilogram objects, and the previous research typically considered targets only in front of the robot, neglecting the dolls behind it. So we also included the targets behind, and we reach all the targets 5 centimeter accuracy. Here, more challenging scenarios. As you can see, it's impossible to model that kind of an object. It's like heavy, you don't know the friction coefficient, friction distribution at all, and we use that kind of a setting, and also we kind of poke robot more and create disturbances, but still you are able to reach the target. So in the video, Do you also see the RV's visualization? And what if the robot is no longer equipped with a tactile sensor? Can we use the same controller with other sensor perception hardware types? So in response to that, we propose a novel sensor substitution approach using a machine learning techniques to enable manipulation in the absence of original sensor information, in our case, tactile sensor, because not all mobile mice is equipped with tactile sensor, and maybe this controller may use with other sensor types. So we wanted to test that. So this is the overview of the framework structure. The key aspect of the sensor substitution approach is developing effective yet computational lightweight pre-processing method for the data coming from the available alternative sensor. So it is important to pre-process the raw data. Feature extraction is necessary. Within our contact perception module, we employed regression and classification-based long short-term memory LSTM networks to predict the contact location and contact type. And this brings us to the point where we can mimic the output of the absent sensor, the contact sensor here, and use the same robot controller even when working with different sensor modalities. So here, as a baseline, you can see we have pushed the object with the contact sensor, the tactile sensor. And as you can see, when the RPS operates the contact perception module estimations using a LiDAR sensor instead, we were able to push the object for all the target locations, both for the same targets and the targets that are not included in the training set. And when we use RGBD camera instead of LiDAR, without additional training, like with the same trained network, mobile robot was able to push the object with the 86 success rate. So it's kind of a generalizable. And the new approach enables manipulation also for lightweight or deformable objects, and it overcomes one of the inherent limitations of the capacitive sensor that we used before, because like you need a certain pressure to detect the contact. But this ability to use different kinds of sensor like open another way, another door to manipulate all kinds of objects, even for the deformable ones, lightweight ones. Here you could see we are again disturbing the system. Test. And lastly, dynamic center of mass perturbation. So the inertia of the object always changing. Yet it adapts. I would like to thank my team and my supervisor, Arash Vujudani, for his valuable guidance and continuous support. Also, I would like to thank especially Doğanay Şirintanov, who has been my companion in this robotic journey from the first year of the university until now, and continue to be part of it today. Much of the work together, he was also the author. And lastly, thank you all, and bye-bye at the same time. I hope our paths will cross again, maybe in person next time.